All right, what is going on, party people? It is almost time for Advent of Code day 3. In fact, if I pull up browser here, let me look. So we have 16 minutes to go. Let's get our leaderboards. I'm probably nowhere on it. That's fine. I'm very slow at these, but that's not the purpose of this. I'm just having some fun documenting my process. So you can see we have 4 stars so far. I have no doubt we'll be able to complete day 3. Just some updates on my framework. I've kind of developed this framework over the last few years. I don't like doing the same thing more than once, and there is a pattern with Advent of Code where everything is what I was calling a grid. I've renamed this into a matrix, and I renamed some of my variables. So we have a matrix of strings, which is just a slice of string, and then we have a matrix of ints and a matrix of floats, which are just slice of those things. And there's ways to convert, well, from string to ints and from strings to floats. I don't really have a back to strings method, although I'm sure I could create one. I'm utilizing some generics here. One of the things that kind of bothered me was I was doing a lot of conversions between bytes and strings. And ultimately, if they are bytes, we can treat them as strings. We could maybe think about doing this just all as bytes, and maybe I'll come back and modify this later to kind of optimize it. But really, this is kind of micro handling, micro optimization at that point. So I changed this from like as grid to new so that the flow inside of I've also went back and refactored like day 1. So now it's matrix.new, which is going to always return a matrix.strings. And then you can rotate them. I did add and update the rotate method so that if you have an unbalanced grid, so you have more columns than rows, or more rows than columns, we can rotate them. I just kind of cheated a little bit here. This is the more optimal way to do it if we have rows and columns that are equal. And then I just said, hey, if we're unequal, go ahead and rotate them unequally. Yes, I do realize that, we might have different lengths and columns across the board and etc. It's not something you commonly see in Advent of Code, so I'm not going to worry about it. But this is for my kind of laziness. So this gives us the ability to take some input from a file, create a matrix, rotate it, convert it to floats, do some things on it. The reason I rotate here is because this was a set of columns, and for me, it's just easier to think of things as 2 rows of data. So I'm rotating it so that those 2 columns become 2 rows with a column value for each value. The other thing here to kind of keep in mind, one other update I did was I created this common run method. So instead of having all that logic about the different file inputs, this will essentially create the file, read it, execute it. I did have to do a little bit of some interesting things here, but essentially we're just scoring the part and then kind of outputting the value based on the type of the function. So if our function puts out a float, or if it puts out an int, or if it puts out a string, really doesn't matter. That data is there for us anyway. So this tightens this up so that we can just run, execute those given functions on those given parts, those given inputs. And that's pretty much it. Most of it was refactoring to kind of fit into that paradigm. So we know that if we're dealing with a matrix, we can just new it, rotate it, float it, etc. So this simplifies our parsing a little bit. Now I do know from previous advent of codes, sometimes they'll give you like a separated file by like hard return, and then, or you'll have blocks separated by 2 hard returns or 2/n's, and each one will be a separate input or grid. And then sometimes you have to do things with multiple grids. We'll worry about that when we get there, but we should have enough of a framework here to kind of make that easy. I also added a counts method that just takes in a comparable and creates the keys with the counts. That was pretty straightforward. I've had some other functions in here that I haven't used since previous AOC, so I have to keep them in mind. But as in SAS floats are just helper methods to kind of get us into the right data types. And then yeah, floats and ints are pretty much that. And that is really that. I mean, though I didn't do too much work. I just kind of refactored some things, generalized some things, and moved some things around. So that sets us up for day 3. I've already built out. I'll just show you day 1. Oh, this is wrong here. Day 1 still works. We're not worried about that right now. We're focusing on day 3. And as you can see, our score is currently 0. And this is where we will be writing our input. We also have a test stubbed out here. And we can really decide how we want that to be once we see what we're dealing with. I did struggle a good bit yesterday, mainly because I had a optimal path in mind, and somebody did comment and say that I was optimizing too early, which was true. And really not because I didn't see a more optimal path. There is a more optimal approach, and I can even probably make it more optimal than it already is. But rather, doing it the brute force way gave me the ability of seeing the actual result so that I could test and compare the 2 outputs so that I could take a more optimal solution and improve its accuracy. So I was optimizing too soon. Wasn't necessarily a bad move, but it did waste some extra time long term because I didn't know what the right solution was, and I was having a hard time finding the bug. So what was yesterday's solution? The brute force solution in part 2, you were allowed to, in part 1, let's start there. There were certain parameters that would mark something as unsafe. These unsafe things were if the slope ever changed, or if there was a difference between 2 values of 3, or if the diff was 0, meaning we were flat. So either too high, too low of a slope, or flat, or if we went up and down, right? If it was a wave. So using this, we were able to determine the first one was just we weren't allowed any unsafe tests or levels. And so that's pretty straightforward. We just say, hey, do we have any unsafe index? And if so, or if not, what -1 will return, and then our score is incremented for that particular one. Part 2 was a little bit more challenging because we were allowed to remove one unsafe index. And so I had this more optimal plan in mind, but the brute force method is just go ahead and check to see if just take your input, and if at any point just remove one of the indexes. And if we do not have an unsafe index, we're good to go. And so you can see here that we would just iterate through that. We'd always remove the first one, and we would go in and run it with one less. And then we would do that every time. And then if that didn't work, we would move forward, remove one index, etc. We wrote this, and once we decided to do the brute force, we had this done and tested and proven in maybe 10 minutes, which then gave us the difference of 4 records. And we came back, and as we investigated, the issue that I had was I was returning the wrong index. I was returning I here instead of I minus 1. And because I was returning I, we were getting actually the index after our unsafe. So when I was attempting to remove previous and next and current, I was actually one index forward than I needed to be. So adding minus 1, since we offset at 1, this allowed us to guarantee what our checks were. So that is that answer. Just kind of a review on yesterday and what the solution is. We proved, obviously, with benchmarking that this was faster. One note is knowing the input, with the pretty deterministic length, I think of 8 numbers, randomizing once an unsafe index is found, and just continuing through and deleting and guessing, or not guessing, but it's not really randomization either. It's just linearly going through them is not bad. Had these number lists been much larger, going farther out to the right or farther out to the left, we could find that a more optimal solution would have been needed here. At one length, I'm not sure, but I'm used to dealing with a lot of input data and a lot of values at different lengths. So I wanted to kind of take a first step approach and kind of see how optimal I can make it out of the gate. That, of course, did lead to me spinning my wheels for a little bit. So we're going to try not to do that today. I don't like to get some sleep tonight. And mind you, I didn't end super late last night, but I did find myself playing some Black Ops. Is it 6? Whatever the latest one is. And I live on the East Coast. So it's a balmy 40-something degrees outside in Florida. So great weather. All right. Yeah. So I've talked a little bit about my keyboard. And, I'm doing pretty okay. But this is my new keyboard, the ZSA Voyager. It's a great keyboard, low profile. I can bring it to work. My only complaint is the cords. I do like a Bluetooth keyboard, but other than that, it is working quite well. This is actually how I set mine up on my desk here. So I kind of keep one to the left, one to the right, and then I have the space in the center. I actually use my mouse off to the right still. But this is kind of my setup here, or very similar to. The one thing that people, you don't realize out of the gate is with this design, you can shift the keyboards on the left and the right slightly so that if you have wrist issues by moving your keyboard around in different positions, different orientations, you get a more comfortable wrist, less stress on the wrist, things like that. Pretty cool though. anybody's interested, I can give more of a walkthrough as to the things that I've noticed and the things that I want to change as a programmer, but I'm not quite there yet. We've got 1 minute and 55 seconds left. So I think we're good to go here. I guess I can get those set up so I don't have to reopen them. And then I'm trying to think if there's anything else I want to do here. It's a little unfortunate. I guess I could... I have a much larger screen, but I feel like if I use my main screen, that the resolution on the text might be smaller. I don't like all these window switching. Maybe I can do something like... I kind of want to do something like that, actually. All right. 15 seconds. Yeah, let's do that. 3, 2, 1. Here we go. Day 3, mull it over. Our computers are having issues, so I have no idea if we have any chief historians in stock. You're welcome to check the warehouse, though, says the middlely flustered shopkeeper at the North Pole toboggan rental shop. I can't say toboggan. The historians head out to take a look. The shopkeepers turn to you. Any chance you can see why our computers are having issues again? The computer appears to be trying to run a program, but its memory, your puzzle input, is corrupted. All the instructions have been jumbled up. It seems like the goal of the program is just to multiply some numbers. It does that with instructions like mul x plus y, where x plus y are each 1 minus 3, are each all 1 through 3 digit numbers. For instance, mul 44, 46 multiplies 44 by 46 to get a result of 2024. Similarly, mul 123 4 would multiply 123 and 4. However, because the program's memory has been corrupted, there are also many invalid characters that should be ignored, even if they look like part of a mul instruction sequence like mul, or do nothing. For example, consider the following sections of the corrupted memory. X mul 2, 4, do not mul 5, then mul 11, mul 8, 5. Only the 4 highlighted sections are real mul instructions. Adding up the result of each instruction produces 161, 2 times 4, 5 times 5. Okay, scan the corrupted memory for incorrupted mul instructions. What do you get if you add all these results of the multiplications up? So, it seems like I could just do some sort of regex here and pull out. That should be pretty straightforward. So if my input is this, did all that work too? But let's go ahead and come here and let's just update our test and let's do our input. Already have it up here actually. Test is this, and our result for that is going to be 161. So we can put that here. You know, we can do 0.0. Let's run that. And we get a fail, not expected 161, actual 0. Okay, so then what we want to do is just look at this and we can build a regex pattern. So we actually can look for mol slash, and then it was 1 to 3 digits. I suspect that's important because we need at least 1 digit, but anything, if we have 4 digits, I don't think that would be valid. So let's make sure we consider that in our testing. So, okay. So what we can do then is we get our input. Let's create a regex remol. We can use regex p dot must file. So I'm gonna do this like this is how I like to do my regexes. So the compile step of a regex in Go can actually take quite a while. What I mean by that is that if you're doing it over and over and over and over and over and over again, it can just compiling it can actually be costly. So what I like to do is if you use this must compile, you can put that and declare it as a var, and then yeah. Yeah, so we can declare once, we can compile them once, then we can search through a string for all of those particular matches. But then we want to capture out the D's, the values here. And so remind me, let's do Golang regexp capture groups. I'd rather not just parse it out. I might as well just do it right. Oh, good old Golang here. Capture group. Okay, so I think I have to actually escape these out. And then we're gonna go ahead and we're gonna and then we want these to only be, I think you could do, instead of this, we could do 1-3. Is that how you, let me get rid of that. So then we'll go with, I think this is true, but I just don't remember. Oh, it's a comma. Okay. It's not something I do quite as often. Okay, so then we can do, so now that we got that, let's do for re mol dot find all, find all and then our input is s. What is n? Indicates no match. What is n? It doesn't say what n is. Oh, okay. We'll just call it 0 then. So if we do this, and then we should be able to do, let's just, let's, I mean, we can just define length of S, right? I mean, okay. Let's just do that real quick, and then let's see. Let's get an idea of what our output's going to look like here. So 109, 117. Let me stringify that real quick. Mul 2, 4, mul 5, 5, mul 11, 8, mul 8, and 5. Oh, okay. So that's our matches. But what's the other function? Oh, that's find all, but I think I want to find all submatch. Because that should be a slice of byte. What does that do? Well, completely unreadable is what that is. So, okay, so if we call this submatch, I think we'll have like a multi-part, yeah, something like that. Yeah, 2, 4. So the first index is just going to be the match, then 2 and 4 are the two values. So then what I can do then is just simply say, okay, because we have a match, I can say parse int string dot parse float, and we'll call it string match sub 1. 64. Okay. And then should it be F1 times F2? Score yeah, so I think this should be it right here. Let's try it. Parse float. Ah. There we go. Cool. All right, so that should be part one. So we take our input and we place that in our one. Is that 6 separate lines of input though? Hmm. Okay. Did I consider that? No. I just considered the input of the bytes. But that should be fine because this is going to be a multi-line file. So I should be able to just run part one. Let's see what this input gives us here. Awesome. On to part two. All right, part two. As you scan through the corrupted memory, you notice that some of the conditional statements are also still intact. If you handle some of the uncorrupted conditional statements in the program, you might be able to get an even more accurate result. There are 2 new instructions you'll need to handle. The do instruction enables future mul instructions. The don't instruction disables future mul instructions. Only the most recent do or don't instruction applies at the beginning of the program. Mul instructions are enabled. For example, mul, don't, know the muls, do, muls. This corrupted memory is similar to the example from before, but this time the mul 5.5 and mul 11.8 instructions are disabled because there is a don't instruction before them. The other mul instruction functions normally, including the one at the end that gets re-enabled by a do instruction. This time, the sum of the result is 48. Okay, so interesting. Okay, that's fun. There's 2 ways we can approach this. The first way is if we get any of the text in between a don't, because anything to the left is automatically a do, a don't and a do, even though that's undo, that's interesting, a do, if we get in between there and we delete that text, that leaves us with the remainder of just the things that are mullable. I kind of like that approach because we can get the indexes of the don'ts and the do's. And we could just scan it and say, okay, give me the first don't. Okay, index forward until the do. Move that. Find the next don't. Index forward to the next do. Remove that. And if we reach the end, remove everything from the index of the don't forward. I'm trying to think if there's another way to do this. We might be able to do a complex regex, but I think pre-parsing it makes the most amount of sense to me. So part 2 it is. All right, so we're going to go ahead and place this here. We've got the don't and the do. And we know in our test for part 2, we'll go ahead and undo this, and we'll undo this. And we know our expected output for the test is 48. And so what's cool about this is with this approach, I can actually leverage part one in part two. And so part two becomes, let's do it like this, pre-process text. And then it is literally part one passing in whatever S is, right? So if we do something like, let's see here, remove, let's call it clean. I think this is the way we're going to do it. And we'll call S equals to clean, and clean receives an in. We'll call it clean, and the in is a slice of byte, and the out is a slice of bytes. Right, so for so we can do just a for, like an iterative for loop, an endless for loop, but we'll say for dot index returns the index of the first instance of separator in S. And so we want anything that, so our input is in, and our separator is going to be right? That's what if we look at our example here, that is don't, as this is written here. Right, okay. Okay, let me actually just, let me undo this a little bit. This is a little confusing. I do like where this is going. I was trying to not do this twice. Let me just do it the simple way first. We need to do this as there we go. If we find the index of don't, we know that we need to do something. So let's do, we'll go with this. -1 will break. So if we don't find a don't, we're in the do, right? So we'll establish that. We have a don't, then we need to check for an end. This might be a little just whatever. So then we want to return whatever our in is up to the beginning, right? So that's where the first index of don't is. We want to return up to that. Else in becomes so we can do slices dot delete, and our input can be in and begin and so what this should do is it should go back up and reiterate on in, and if we find another don't statement, this needs to be do. So if we end up in a don't, we want to go until we have a do. And that's pretty much it, I think. Let's just try it. Right. Part 2. Oh, score. Actually, there we go. We can get rid of this. Let's just make sure this is set up correctly. Let's reduce this down further. Expected 48, actual 0. Okay. Let's just make sure I have my do statement correct here. Make sure my test 2 is my test 2 is not populated. What did I do? I put it here. Oh, I put it here. Okay. Hopefully that was the issue. Yes. Okay. So now we come back here. We get our puzzle input. Don't know if it's the same. Usually is. Don't really care. Run that. And then I think we need to do one last thing. If I didn't do it, is part 2 and part 2. Going for broke. Oh, did I accidentally? Panic, runtime error, slice out of bounds. 1263:88. Okay, let me look at this delete function because I think this is fine. I just think I don't understand I don't understand. Delete removes the element si colon j from s, return the modified slice. So if j is greater than length of s or sij is not valid slice of s. So if many items are deleted, make a single delete, one at a time, delete zeros the elements. Is that I don't think that's it. Is that what you're wrong? No. So what did I do wrong here? So if end is -1, slice bounds out of range. Ah. If the first do, okay. Ah. Okay. If there's a do at the beginning, or that's the problem. I think if there are multiple do's in front of a don't, yeah, I do have that scenario. So, is there like an index? Hmm. I mean, okay, we can kind of maybe cheat this by saying begin that, and then maybe it's begin plus end. I think maybe. Let's run the test and see if the test passes. Okay. Let's see. All right. Let's see if we got it. Awesome. All right. That's part 2 complete. So to recap what we did here, we'll just kind of walk through it. I'll kind of walk through my logic. So we had, first off, it's just a basic regex problem. I do some regex freehand, but I don't have all the syntax locked in memory, so quick Google search. But we need to identify specific sets of data, and that was part number 1. So anytime we had a mul operator with digits between 1 and 3 numbers, we need to parse them out, multiply them, add them up, and that was our score for part 1. For part 2, it was the exact same thing, but we have this don't and do block. So anytime we saw we start in a do block. Anytime we saw a don't, we wanted to disable the function until the do block. So there's a couple different approaches. One is we could have just stepped through, and anytime we found that index, we could say, okay, don't process these blocks. But in this particular case, we really don't even want to step through or regex that data anyway. So I thought it would be better for us just to pre-process that data. So I created a method called just clean, not great naming convention. But the idea here is that we would take our input and we would get our begin index and we would get our end index. And then the one trick here is that, you know, there in some blocks, there were do's in between or previous to the don't. So when we look for our do, it has to be after our don't block. And that was, it hung me up very shortly, but quick fix here is just to say, okay, look in the in slice and start at the beginning. And then that is our section that we delete. And then we're just deleting out the blocks that don't matter every time, reducing down our input set. So then our part 2 is simply calling part 1, but with a clean function on it to sanitize out or clean out that data. And that really is all there is to it. We're done for today. I doubt I'm anywhere on the leaderboards, but we can look and laugh at how maybe. So I am 132. No, wait, who am I? Anonymous user 21. Oh, let's go day 3. 2. I'm probably not in here at all. What did it tell me? Does it tell me where I ranked? That'd be nice if it just said you're terrible. You rank. You reek. Oh, no, these are just the first 100. Yeah, definitely not in the top 100. They did this pretty quickly. 1 minute. Oh, did you guys not even read it? Is that what you did? Is that what the strat is here? Just don't read. Okay, so there is another board here I like to look at. Oh, the stat board. There we go. Oh, I mean, I was in, you know, just 4,000 people who've actually solved it so far. It's, you know, it's crazy. Yeah, whatever. That's interesting. So, it'd be nice to know where I rank though. Anyway, it doesn't really matter. I'm not doing this for speed. I'm doing this just to think through the problems. That's it for tonight. I'm going to end the video here. It's a nice little short one. Maybe I'll go play some COD still. I don't know. But thanks for joining. If you have any questions, comments, or feedback, feel free to leave it here. I may publish this at some point. And didn't use my matrix code tonight, but that's okay. I think we'll probably be using it a bit more in the future. All right.